again, class. I'm glad you've joined me for the second set of our momentum unit. So our first thing that we're going to talk about is how does momentum relate to force, okay? So we're going to specifically talk about a soccer ball, okay? So I have a soccer ball rolling towards me. If I want it to stop, what do I need to do? Right? I need to apply a force, okay? So I have some soccer ball, it's moving this way, right? That's my velocity. I need to apply a force in the opposite direction to cause it to stop. So we're going to kind of think about how much force does it take to change a particular amount of momentum, right? Because this has a mass and a velocity. When we initially talked about momentum, we said it has to do with how much do you need in order to continue moving forward, right? And so the other aspect of the idea is how much force do you need to stop something from moving, okay? So let's talk about Newton for a second, okay? His second law, the way we always write it, is F equals ma, okay? But we can actually break this down a little bit, okay? Acceleration. What is a formula that gives us acceleration? Does anyone remember? Go ahead and pause the video and take out your formula sheet, okay? And see if you can find a formula for acceleration, okay? So I'll give you a second. Okay, hopefully you came up with something that looks like this. Vf equals Vi plus At, okay? If you had a different one, that's great, but this is the one we really want to look at today. So first of all, we need to solve for A, because we have A here, and I want to plug this formula into this, okay? So let's subtract this, so I have Vf minus Vi equals At, and then I'm going to divide everything by T, okay? So that leaves me with just A equals Vf minus Vi over T, okay? So now what I'm going to do is I'm going to take this and I'm going to plug this in here, okay? So I get F equals mVf minus Vi all over T, okay? Now, I'm going to take this T and move it to the other side, and you'll see why in a second. F times T equals m Vf minus Vi. Okay, now the parentheses kind of obscure what's going to happen here, so I'm going to do one more step and I'm going to multiply out the n. So I have F times T equals m Vf minus, oops, actually need to distribute, minus mVi. Now, this right here, does that look familiar? Anyone? Does that look familiar? Of course, right? That's just our formula for momentum, m times v, right? But I'm specifically using Vi. So what kind of momentum is this? Yeah, it should be my initial momentum, right? So another way I could write this is F times T equals the final momentum minus the initial momentum. And I could also write it like this. F times T equals delta P, the change in momentum. In other words, we can take Newton's second law and show how a change in momentum, right? We're talking about how do we change this momentum? How do we change what it's doing? Is just equal to the force times time. So if you want to change a momentum, you need two things. One is a force, and you need to apply it over a length of time. And you're just multiplying these two things, okay? So we've actually defined this, and we say F times T is equal to impulse, which is J, okay? You might also see it as I sometimes, but I believe your formula sheet calls it J, okay? Now, remember, what were our two units for momentum, right? We had units for momentum were kg meters per second squared, right? That's kind of the one we could see because mass is kg and velocity is meters per second, right? And then what was our other one? Our other one was newtons times seconds. So here you can see newtons times seconds is equal to a change in momentum. So they need to have the same units, right? So that's kind of where this is coming from. So usually we use this for momentum and this for impulse. Okay? So, our formula, I'm kind of giving you a lot of different versions of this formula. The formula is usually used like this, okay? Where I have my force times the time is equal to the mass, and I sort of have it factored out of velocity final minus velocity initial, okay? This is usually the easiest. Sometimes this isn't a bad way to go, but it's also helpful to keep this in mind, okay? Because I want to have that idea that if I want to change a momentum, I need to take a force and multiply by a time. Okay, now let's think about how does this practically apply. Why is follow-through so important in sports, right? If you've ever been in a sport, you've probably heard something about follow-through, right? If you're hitting a volleyball, you want to make sure you're swinging through, right? If you're throwing a ball, you need to make sure you're doing this, right? You're following through. You don't just kind of, you want to continue your motion through. And so this idea of continuing through, the reason we do it is because of this time part, okay? If I want a ball to go farther, okay, hitting a ball, right, I need to change its momentum. And I want a big change in momentum, okay? There's two ways to do that. One is to increase the force, right? So that's going to the weight room, going to CrossFit, getting stronger, right? But this takes time, okay? The easiest way is to change how you're throwing. If you just throw like this, how much time are you in contact with that ball? Very short time. So your change in momentum isn't going to be very big, and it's going to go pretty slow. On the other hand, if you have a full motion, right, then this time is going to be much bigger. And you're going to be able to change its momentum much more, which means it will move faster. Okay? This is why follow-through is so important. You have a longer time, which means the ball will go faster. Let's go ahead and scroll down and look at a problem. Okay, we have two problems here today. So our first is we have a car that is crashing into a utility pole. Okay, so a 1,400 kg car is moving eastward with a velocity of 15 meters per second. And it collides with the utility pole, and this car is brought to rest in 0.3 seconds. Find the magnitude of the force, so we're looking for force, exerted on the car during the collision. So let's write down what we know. Okay? What is the mass of the car? Yeah, the mass of the car is 1,400 kg. Okay? What is my initial velocity? Yeah, the initial velocity is 15 meters per second. Okay? Now, remember, last time we said the direction is going to matter. So let's go ahead and set up some axes. So, got left and right. And it is moving eastward. So I got west, east. Let's make eastward positive. Okay? So this will be a positive, this will be a negative. So this should be a what? Yes, this should be positive. Okay? Now it is brought to rest. What velocity is rest? Yes. The velocity that is rest is 0. Okay? So that needs to be my final velocity is going to be 0. Okay? Now, what is another variable they tell me? What's that last variable? Yes, the last variable is going to be time. So t equals 0.3 seconds. So it didn't take a very long time, so a very short collision. Okay? If it's a short collision, what do you expect about the size of this force? It should be a pretty large force, right? The shorter the time, the bigger the force. Okay? So we got this, and what am I trying to find? I gotta find that force. F is my question mark. Okay? Now let's go ahead and write down our formula. So the one I recommended you use was F times T equals M, and then I have VF minus VI. Okay? So this is what I'm starting with. Let's go ahead and plug in. So F is what I'm looking for, so I keep F times what? 0.3 equals what? Yeah, 1400 times, what was my VF? Yeah, my VF is going to be 0 minus, my VI is 15. Good. Okay, so I got something like this. This will just give me a negative, correct? So I'll have 1400 negative 15 equals F times 0.3. Okay, so what's my last step that I need to do to solve for F? Yeah, I need to divide by this. Okay, so I'll have F equals 1400 negative 15 times negative 15 divided by 0.3. Okay, so this is the part where you're going to pause, take out your calculator, and solve for F. I'm actually going to grab a calculator as well, so I can find a number for F2. Okay, so 1400 times 15 divided by 0.3, and I get 70000. I get a negative. Okay, so now we need to think. Does a negative make sense? Does that seem weird that we have a negative? Well, let's go back to our axes. The car is traveling initially in this direction. If I want to stop the car, which way do I need to exert force? That's right, I need a force backwards. So this is my force. This is my velocity, okay? So a negative force is this way. So the best way to usually write this then is to say F equals 70,000 newtons, and then just give the direction. Remember, I don't want a double negative, so I don't want a negative and a west because that really means east. So I'll just say 70,000 newtons west. Okay, and that's my final answer. Let's go ahead and look at this second example. Okay? I have a 2.5 kg ball strikes a wall with a velocity of 8.5 meters per second to the left. The ball bounces off with a velocity of 7.5 meters per second to the right. Okay? If the ball is in contact with the wall for 0.25 seconds, what is the constant force exerted on the ball by the wall? So let's go ahead and write down our variables. Okay? What's my mass? 2.5 kg. Okay? What's my initial velocity? Yeah, so that's going to be 8.5 meters per second. And it says to the left. So let's go ahead and draw our axes. Let's make the right positive and backwards left negative. Okay? So this one is originally to the left, so that's going to be a negative. Okay? Now what's our VF? Our VF is 7.5 meters per second to the right. So that's going to be 7.5 meters per second. And that's going to be positive or negative? Yeah, this one's going to be positive. Okay. Now, if I'm initially moving this way, okay, so this is my velocity, which direction do you think our force will be? Yeah. In order to switch the direction of my velocity, I need a force in this direction, right? So we should expect a positive force, not a negative force. So I got my VFs, my V on VF, and I also have the time. So what's the time the problem gives us? 0.25. Okay? And then finally, we are looking for my force. Okay, so that's what I'm looking for, right? Okay, let's go ahead and write down our formula. So we still have the same formula from last time, so we can still use this again. F times T equals M VF minus VI. Right? So let's go ahead and plug in. Force is what I'm looking for, right? So I just write F times T is what? Yeah, my T is 0.25 equals, what's my mass? 2.5. Okay? And then I have VF, which is 7.5. And then I minus, right? But what's my VI? Negative 8.5. So I have minus a negative 8.5. And minusing a negative is just adding, right? Okay? So I have F times 0.25 equals 2.5. and then I have 7.5 plus 8.5, so that should give me 16. Okay? So, to solve for this, I just need to do f equals 2.5, 16, divided by 0.25. Okay? Now I'm going to see if I can do this in my head. Give me 1 second here. Okay, apparently I cannot do it in my head. So let me take it out of the calculator as you take out the calculator. So grab your calculator. If you need to go grab it, pause and grab it. Okay, the correct answer is 160. And what are the units for forces? Yes, newtons. Good. So that's my final answer. Okay, now, what is the sign that we got? Positive, yes. And remember, that makes sense because I am expecting a positive force. Okay, go ahead and scroll to the first question, and I'll give you a chance to work on it, okay? So I'm going to scroll up. Let me erase a little bit so you can see a little better. Okay, a pitcher throws a curveball to the catcher. Assume that the speed of the ball doesn't change in flight. Okay? We want to know which pitcher exerts a larger impulse and which player exerts a larger force. Okay? So go ahead, pause your video, think through the ideas. Remember, focusing on the formula we just learned, and see if you can answer this correctly. So go ahead and pause the video. Okay, so let's talk about this. Let's see if you got it right. This is actually kind of a trick question. Okay? So the impulse is F times T. But this doesn't really give us much information on which one of these impulses was larger. But delta P actually will give us a really big hint into which one is bigger, right? So we have this ball. The pitcher initially, the initial velocity of the pitcher is going to be 0, right? Before he throws it, it's just 0. Then at the end, let's just say it's 40, okay? 40 meters per second, okay? So this is what it is initially, and we have the same mass of the ball, okay? So his change in momentum will be m, it'll be 40 minus 0, okay? So it'll be 40m. That will be his change in momentum. Okay, so his impulse will be 40m, 40 times the mass of the ball. Okay, now, so this was the pitcher. Okay, now let's look at the catcher. Okay, the catcher, his initial velocity is going to be what? Well, it doesn't change during the flight. So it's got to be whatever it left the pitcher's hand at, right? So his initial velocity is going to be 40. Right? So this is as he's catching it, right? It's coming at him right before he hits his hand, it's going to be 40. Then it's going to start slowing down once he catches it, right? What's the final velocity? So he catches it, hits his hand, and eventually should stop, right? So what number should this be? Yeah, this should be 0. Okay? And obviously we have the same mass. So his change in momentum, right, is going to be this Vf minus Vi m. Right, which is sorry, where this is coming from, right? mvf minus vi, right? That's the change in momentum, okay? So I have something like this, just m, and then this one is going to be 0 minus 40, okay? Right, so this actually gives us negative 40m. Now, the negative just tells us what? Negatives and positives always tell us what? Direction. So as far as the magnitude, right, we don't really need to worry about direction. So I'm going to get rid of this negative for a second, okay? Which one of these is bigger? Yeah, see, that's the trick question. They're the same size. So both players will have the same impulse. Okay? So both players. Now, which player exerts a larger force? So one way to think about force is which is more painful, right? If something hits your hand with a lot of force, you're going to feel pain, right? So if you think about it, is it ever hurt your hand where you're exerting the force to throw a ball? No, that's pretty unlikely. But if a ball hits your hand, that often hurts, right? So which one do you think is the bigger force? Yeah, the catcher is going to exert the bigger force, okay? Another way to think about this is what takes longer to do, this whole motion where the pitcher is throwing, or the catcher where it's just right, that very short amount of time as it hits his hand and stops. Well, the catcher is going to have much less time where it's going to go from moving to stop. Whereas the pitcher has a long windup to throw the ball, right? And that follow through. So if I have this F times T, the catcher is going to have a very short amount of time, and short time means the force has to be much bigger, right? Whereas for the pitcher, I have the same setup, F times T, right? His time is pretty long, right? It takes a little bit of time to throw a ball, okay? Which means his force will be less, okay? Remember, both of these equal to the same number, right? This impulse, this change in momentum is the same for both, okay? Go ahead and work on finishing these problems. Make sure if you have a question, you can look at the answers that are there in that folder. Alternatively, if you really get stuck and you need some extra help, send me an email. Thanks for tuning in to our set B, and I will see you in a couple minutes for set C.